My name is Ivan Korshunov. Today I will tell you about some limit theorems for spread of disease. Firstly, let's talk about model. We will work with discrete time CIR model, which is, maybe some of you know, is susceptible infected removed model. These models are very popular in modeling some disease spreading. We will have population of n individuals. In the beginning of our process, only one individual will be infected. Then every infected individual makes k contacts with other individuals. Contacts can be the same. They can repeat. So every other day, person that was infected, contacted by infected person previous day, becomes removed. I mean, becomes infected, and every infected person becomes removed. Then some mathematical model. We consider random sequence y n zn, which satisfies following conditions. Firstly, z0 is equal to 1 and y0 is equal to n minus 1. Z will correspond to quantity of infected person in at the moment n, and y0 is the quantity of not infected and not removed people.
Sum is constant.
Sorry?
Yn and Zn plus Zn is n.
No. Y is people who are not infected and who are not immune, has no immune. Then yn and Zn. Under condition that n minus 1 is equal L, we draw Kyle balls from the urn with replacement, and we just do it. Then we assume that new amount of infected individuals is equal to amount of balls with number less than amount of not immune, not infected people, individuals in the previous day. And yn is amount of non-infected, non-immune people in previous day minus amount of infected people in this day. In such problems, it is common to use some deterministic sequence, so it will be easier to understand what is going on with the real stochastic sequence. So let us consider a deterministic sequence which is recursively defined. Again, y0 is n minus 1, z0 is 1, and you can see recurrent formula for yn and zn. P is probability for one individual to not to be infected by one infected person. For the sequence, we can obtain some results. First of all, YN has a limit, alpha n, and it's also true that there is a alpha n is a solution of the following equation. Also, that is true that alpha n is increasing sequence, which has a limit, which is least root of the following equation. This equation is quite hard to analyze, so I can't say much about alpha or alpha n, but you know they're existing. And at this moment, we can expect that part of people who will be the part of people who will have immune when disease ends, spread of disease ends, will converge to alpha n or alpha or something like that. Here you can see some graphs. This is graphs of alpha n, where k is equal to 2 and 3. As you can see, it grows to some number. Also, here is a graph of alpha of k. Yeah. So main theorem, my main theorem is this one. If we consider the moment of epidemic when epidemic terminates, then part of people who has immune conversion probability to alpha from previous equation as population goes to infinity, tends to infinity. So let's speak about some ideas of proof. First of all, we need to obtain some results for sequence YNZN. Studying this sequence and understand how it changes over time. Then we will try to estimate L2 distance between deterministic sequence and stochastic sequence. And then, according to first part, we can split our process to some parts where it develops uniformly. So first time interval is from beginning of the process to about logarithm n. Within this period, Zn grows exponentially at rate k, about k, and we can we have good estimations of L2 distance from some methods associated with variation distance. Then in the same period, we can estimate L2 distance with some recurrent relations for stochastic sequence. Yeah. Then second period is from logarithm n to logarithm n plus logarithm n inversed. Within this period, there is also exponential growth, but not actually growth. It decreases with rate alpha k inversed. Here again, we can estimate L2 distance with with usage of some relations between stochastic sequence. Here you can see some graphs of deterministic sequence. As you can see, it grow very fast in the beginning, and then it has like plateau or peak, whatever, for 2 or 3 days, and then it decreases exponentially again with different rate. Here you can see these rates. First rate is about k, and second is some number, and it's alpha k, about alpha k. Yeah, then we can see that after second period of time, that n is becoming around constant. So that is true that time time when epidemic terminates divided by time on the screen converges in probability to 1 as n tends to infinity. Yeah. So what else? In this problem, main difficulty is that all methods that are used in other epidemic models can be used. Here, in these theorems, there are a lot of some technical moments that are not very simple. So I don't really know how to use all methods for some another problems, but it might be interesting to think about this problem. For example, when k is equal around 1, or when amount of people that one infected contact with is also stochastic, with mean around 1. It should be much harder and much more interesting. That's all I wanted to say. Thank you.
Вопрос, пожалуйста.
Yes.
Could you please clarify for us
Yes.
the development of your random process? So return please the definition of Yn and
Stochastic or deterministic?
stochastic.
Of course I can. Yep.
And could you please add some words about the nature of this model? Maybe you can show us something. Or draw.
Nature is very simple. Every infected contacts with k people, and everyone that it contacts who hasn't immune becomes infected next day. That's all. So, yeah. Other questions?
Yes. Could you
Yes.
show, please, another question. Could you show the slide about the theorem of the spread of time t?
Yes.
Of the last theorem.
Yes.
Duration of epidemic.
Yeah.
Could you speak some words about the proofs of this theorem? Maybe some steps, because it's, by my opinion, interesting result. And
Proof of this theorem is very similar to previous theorem. Their proofs are pretty much the same. So, yep.
it's hard to understand, of course, it's need to read.
Yeah. Well, when we obtain that Zn at this time becomes certain constant, L2 distance between Zn, I mean deterministic amount.
Yes,
Zn.
deterministic,
Yeah.
yes. You
Small
fix
z.
n,
Yeah. When it becomes certain constant, at this moment, L2 distance between Zn and between stochastic and deterministic sequences is less than n. I mean, divided by n, it converges to 0. So at this moment, stochastic process is a constant too, with big probability.
maybe, but it is, I think it's not easy to prove such theorem.
Well,
Because it's need to read your texts. Do you have a publication?
so as I said, it's very hard to read because of technical issues.
Do
No.
you
Now I am trying to simplify my proof so it can be read more easily.
Thanks. Any other questions, please? And I would like another maybe remark or question
Yep.
about the modeling of your result. As I understand, using your work, it is not possible to modeling the wave of epidemic. You consider one wave on one interval and another wave on another interval and so on, yes? How could we use your approach to model the wave of epidemics? If you see the real applications, for example, or a real rate of epidemics, for example, COVID and so on.
If I think yes, but no. If k is close to 1, if we can obtain some same results with k is when k is close to 1, it can be something like in real life.
No, k, as I understand,
Yes.
what does it mean k? K is the individuals
Yes.
that one
Infected people.
individual
Yeah.
infected, and after contacts,
Yes.
we have
Yes.
k individuals
Yes.
with this disease.
Yes. Yes.
Why?
In real life, k is not so large.
At the beginning of epidemic, k may be very high.
Yes, and in the beginning there is exponential growth.
Yes. So
But then it's around 1, and that's why these results can be applied to real life.